And I'd like to pass over now to Dr. Stephen White from CSIRO, who will take us through the data-driven smart building journey. So over to you, Stephen.
Thanks very much, Tony. So yes, this is the first of three activities being presented today. This one is the Data Clearinghouse activity. And we've got a bunch of presentations. They're themed around the idea of data-driven smart buildings. So in terms of the agenda for this session there, I'll give an introduction, just a little bit of a recap on the Data Clearinghouse activity and really introduce this concept of, well, what is a data-driven smart building? Then we've got a couple of presentations relating to applications for data-driven smart buildings. So we have a international guest speaker, Professor Jin Wen from Drexel University in Philadelphia, the USA, who's an international expert on fault detection and diagnosis. Professor Mehdi Seyedmahmoudian, who is running DCH5 at Swinburne University, looking at controls of buildings using data-driven approaches, and then TK Wang from VBIS, who is running DCH7 project, will be talking about the building onboarding journey and some of the practical things that we've experienced there. So just those introductory slides on what we've been doing. We have this idea of the Data Clearinghouse as a collaboration platform for Australian industry to do data-driven smart buildings. As a collaboration platform, it's a data infrastructure. Think of it as the electricity industry. It's like the poles and wires that go down the street. And the aim here is to bring building operational data from the BMS, data from IoT sensors and other devices, and data from the web, such as from the Bureau of Meteorology and from the National Electricity Market, bring them all into one place, federate them, and structure the data so that it is easy to access, and then make that data accessible via a fine-grained permissioning system to enable analytics providers to provide value-added services. And, you know, it's really designed to be able to enable artificial intelligence, machine learning, and other advanced techniques for analysis. We see this collaboration platform as helping building owners to get control of their data and to be able to provide that easily to service providers. And we see for service providers, if there's a whole bunch of buildings sitting on the platform, then that makes it an easy pathway for them to get their services to market. So it very much is about creating an innovation ecosystem. We had two projects in the Data Clearinghouse relating to the infrastructure itself, and then we stapled a whole bunch of projects that utilize the Data Clearinghouse to that. And each of those projects, DCH4 through to DCH10 there, have a building owner or a site where a demonstration is occurring and some form of app development going on that provides a valuable service. So ultimately, what we're looking at is a world that looks a bit more like what you would expect from your consumer electronics. You have a platform on which services can be offered, and you can go to the app store and you can download your apps and deploy them very easily. And so the value proposition is around data reuse. Collect the data once and use it on multiple different applications. It's around the ability to bring your software to a building and do it without minimal manual intervention. And it's about making data interchangeable with the web in such a way that you can develop novel applications using different data sources which would never ever talk to each other before. And all that's enabled by data standards. And so we're using the BRIC data standard for metadata schema. And we're using the VBIS standard for classifying and tagging assets. So what about this concept of data-driven smart buildings? You know, what is a smart building? And, you know, just a quick scan of the internet, you would find a bunch of different schemes for certifying that your building might be smart. On the left-hand side there, I've got the WIRED score, which is one of the schemes, and that particular certification scheme particularly focuses around the IT and communications infrastructure. Can you get good mobile access down in the lobby of the hotel? Can you have a choice of providers, resilience, future readiness, etc. Very much a IT-focused definition of what a smart building is. In Europe, there's the Smart Readiness Index, which is another sort of thing that talks to the idea of smart, but it's particularly in the context of energy and sustainability. And so it looks at these different impact criteria from energy, maintenance, comfort, etc., and particularly how they relate to particular services that would happen inside a building, from heating, hot water, cooling, ventilation, etc. So that's much more of a sustainability rating. Now, I'm not here to sort of say which one of these is best. I don't think any of them have got huge traction at the moment. And what would be the right way of bringing smartness, and why we would bring smartness into buildings is, I guess, a hot topic for discussion. So in terms of smartness, this is something that we've been agonizing with in the International Energy Agency, and can we help with these definitions or certification schemes with particular focus on energy efficiency and climate change? We all know that you can't manage what you don't measure, and so the energy meter has been core to the energy efficiency mantra for a long, long time. But what we're saying here, I guess, is that a smart building will have access to much more granular data and diverse data to be able to make sense of what the energy meter is doing. So IoT sensors, building management systems, and the ability even to take it from a portfolio perspective is to address link data. That needs to get brought into the cloud and managed there with data federated and making data accessible via queryable databases and a permissioning system that manages any security issues. And once you've got that, you can start to apply data mining and other analytics techniques. In the IEA Annex, we've got particular interest in model predictive control, fault detection and diagnosis, and grid interactive buildings. And similarly in iHub, these are kind of the topic areas where we can create flexible demand as a service to improve the value of renewable energy. But all that information and modelling goes nowhere unless it can get brought back to the building and brought back in a form that is utilisable by humans. And hence this sort of idea that it's about automation, but it's informed automation where humans can intervene to achieve the outcomes and business rules that they're looking for. We know of these systems as platforms or marketplaces for stakeholder participation in the context of energy and smart buildings that are designed for energy. We would say that rather than the energy meter, it's about having an energy management information system, EMIS. And that's about bringing transparency to the buildings. It's about bringing the maths and all those sort of machine learning type tools, but it's very much about connectivity, both to markets and having machine-to-machine communication. So we asked the question in the annex, what is a data-driven smart building? Got a lot of, yeah, what's that kind of comments. And we broke into groups and talked about this. So we felt that it was about hardware and software interacting in real time, two-way information flows, automation and control, and particularly being able to do things in a way that takes account of benchmarks and baselines. But the buildings had to have data pipes to make that easy to happen. And there was strong concern over data quality issues. And so management of the first parts of that previous circle diagram was seen as pretty critical to a data-driven smart building as an enablement. The applications, as we talked about before, but looking into the future, to what extent will occupancy and some of the things, user behaviour, things that are going on inside buildings, to what extent will that be important in the energy discussion, and to what extent will that bring value to any energy management information system? And certainly coordination from a systems perspective. So it's not just about an individual building, it's how that building activates in a city precinct or in a electricity market. So these were some of the ideas that we tossed around, and in today's session we'll explore two of those applications. That's model predictive control and fault detection, and we'll also explore what it takes to actually get those data pipes happening in some example buildings. So hopefully that gives you a little bit of sort of context for the theme of what we're trying to talk about here. And as I said, we have three fantastic speakers to talk to their experience in this area of data-driven smart buildings. So without further ado, I will introduce the first of our speakers. So Professor Jin Wen, she's a professor in the Department of Civil and Architectural and Environmental Engineering at Drexel University in the United States. She's got 20 years experience in the smart buildings field, including application engineering experience with Johnson Controls. And I would consider that she is a world expert in fault detection and diagnosis, building to grid integration, model predictive control, and occupant behavior simulation. And she's on ASHRAE's Research Administration Committee as well, helping to oversee and coordinate all of ASHRAE's research activities. So we're certainly privileged to have her. I believe it's almost 9 o'clock at night for her, and she's sitting in the lobby of a hotel. So rather than have all the background noise, she's given a video to us to play, but she is online and she will be able to answer questions. So I'll pass over now to Jin Wen.
Good afternoon. My name is Jin Wen. I am a professor working for Drexel University in Philadelphia, United States. Thank you for this opportunity for us to share some of our research in the field of data-driven approaches for fault detection and diagnosis. We'll go over the needs and the challenges, especially related to fault detection diagnosis tools and how they are adopted in the markets. And we'll present some of our solutions, and we'll talk about the future directions and the conclusions. So why fault detection and diagnosis? There have been many years of field studies and also research showing that malfunctioning control operation and also building equipment really has increased dramatically the energy consumptions. The numbers that presented here are somewhat a little bit older data, but the research over the past, I would say 20 years have clearly demonstrated that even for new buildings, if you look closely, malfunctioning systems can really cause at least 10, sometimes up to 50-60% of the energy waste, especially for older systems. So what do we mean about by faults? There's some common faults that for most of the buildings you could be able to observe them, such as stuck the damper, stuck the valve. Sensor bias is very common, especially for CO2 sensors and humidity sensors. They're known to drift away from their manufactured kind of accuracy. Coil fouling, compressor degradation, this is like unavoidable over the lifetime of a system. But interestingly, what people have found in the field is that operator faults, such as the operator forgot to remove some of the set point override, forgot to change the occupancy, are very common in real buildings. On the top of that, control system issues such as unstable control or just some of the control strategies that have not been well thought. All of this are fairly common in real buildings. I'm pretty sure people who have worked in the field understand the existence of such issues. So when we look back, we really have quite some research efforts devoted to AFDD, starting from very early, some of the international energy agencies, Annex, Annex 25, 34, 40, all the way, as well as many kind of significant research projects funded by, in the United States, Department of Energy, funded by California Energy Commission, funded by the AIRAH. As a result, we do have quite some existing tools, ranging from simple ones such as just building up the alarms, some very simple fault detections that are very commonly observable by typical building automation systems, up to some more complicated third-party add-on AFDD software. I'm listing some of the existing ones here. And in recent days, the cloud-based building analytics and continuous commissioning software fairly popular as well. Now, when you look closer, however, people do find that there's still a lack of wide adoption of AFDD tools despite the many options out in the market. When you talk with people working in the field, cost has been the major primary barrier that people identify in this field. And when you look closer, the costs are mostly generated by actually the so-called engineering efforts. Although some of the tools out there require additional sensors, the majority of the tools really had larger costs due to the need to configure and also generating rules, generating the thresholds that are customizable for a specific building. Moreover, another issue is the uncertainty of the benefits and the performance of the AFDD tools. A lot of times, despite how sales people are trying to persuade building owners of all the benefits, often it is fairly hard for the AFDD companies to really demonstrate before and after energy savings because they're fairly a lot of times difficult to directly measure. And not to say other benefits associated with AFDD tools. In a summary, if you look at AFDD tools, the benefits are quite a long list. To begin with, you have improved comfort. The temperatures are generally after the commissioning maintained at a better kind of range as desired, which means better productivities, better satisfaction from the users. Energy savings, the field study often demonstrate, as I said, at least 15% of the energy saving. Improved air quality, increased equipment lifetime, especially if you do the proactive kind of commissioning and fault detection diagnosis. Now, the problem, as I mentioned, is it is difficult to accurately quantify all those declared benefits. Cost-wise, as I mentioned, the engineering labor is really a major issue for the high cost from the existing market tools. So at this point, we do believe that the existing AFDD solutions have certain issues. They are mainly focusing on detection, much less on diagnosis. When I say diagnosis, it means that once you find the abnormality, which is the result of fault detection, can you really isolate what is the root cause of this abnormality? The high engineering hours and installation cost, the false alarm often triggered if you are only focused on specific component without understanding certain abnormality could caused by upstream equipments, or if the thresholds are not customized correctly for a specific building. High implementation cost, and also often limited scalability. Again, existing tools, especially those who use the typical rule-based fault detection diagnosis, often need to be customized from building to building, especially for the threshold. That also adds another layer of market barrier. So we do think that the new technology development, especially those in the sensing, communication, and artificial intelligence strategies, as well as machine learning strategies, really present a great opportunity for us to rethink the entire fault detection diagnosis solutions and for us to overcome some of the major market barriers. So my team has been working on developing data-driven fault detection diagnosis for about nearly 15 years. We have over the years generated several generations of solutions. We started with working on the air handling unit fault and detection diagnosis because AHUs are typically low cost yet have a pretty strong impact on the building performance. So at that time, we really focused on generating plug-and-play implementations with very minimum upfront engineering costs. So engineering cost reduction has been our top priority. So we developed a pattern matching principal component analysis for detection method matched with a Bayesian analysis, Bayesian network analysis for fault diagnosis. I'm not going to bear with you with all the technical details. We have many papers that can describe how we did this. Now, as a result, we have a couple major findings. Number one, it is very important to generate a right baseline. What do I mean? When there are new incoming data coming from a system, for example, from the AHU, in order to find detect a abnormality, especially purely using data-driven method, not using rules, it is very important to understand how this equipment should behave when you are happy with its performance. Now, a lot of times, another challenge for HVAC system is that abnormality could be caused by faults, or it can be caused by weather operation. So finding the baseline data that really represent the same weather and operational conditions so that you can make an apple-to-apple comparison is fairly important. So our group has added this pattern matching approach to the entire FDD strategy and really has resulted pretty good performance. In the past years, we have demonstrated the strategy in more than 7 buildings, ranging from small commercial to large commercial buildings, and have demonstrated a good performance, which result in the licensing of the codes to some components. In a later project that was also funded by the Department of Energy, we started to focus on detecting and also diagnosing the entire building data set. Because there are quite some faults, although it occurs in one component, it really has a whole building impact. And a lot of times, especially for small and medium-sized commercial building, the building owners are more interested in understanding the impacts and issues with those kind of faults. When we apply similar thinking strategies from the component-based data-driven FDD for whole building, we encountered high dimensionality. So the existing strategies didn't work that well, and we explored quite some different methods, and we identified a pattern matching method using the so-called SAX, symbolic aggregate approximation, that is really developed more or less for time series data. And we matched that up with the typical feature engineering with the PCA method that we used before, resulted pretty good fault detection for the whole building data set. On the top of that, when we do the pattern matching, the threshold we learned from the baseline data, again in a data-driven way, we found that are fairly powerful for us to adopt in the fault diagnosis strategy. So again, we use the so-called Bayesian network fault diagnosis. Now within the Bayesian network, we typically use the rules. However, the rules we use here has thresholds that are at this point automatically learned from the baseline data. So there's nearly no need for customizing any of the threshold. Of course, if the building is having a completely different control system, you still need to find the right Bayesian network for that control strategy. We then tested our whole building AFDD framework in one medium-sized commercial building. We implemented 30 artificially implemented faults, and we did find fairly good accuracy, nearly 100% of fault detection, and fairly high diagnosis kind of accuracy as well. What is important for us is that there was no false alarm, because again, the field kind of operators have repeatedly warned us that they can sacrifice sometimes the fault detection or diagnosis accuracy as long as the false alarm rate is low. So they really don't have the human resource to handle false alarms. One added benefit of using such data-driven approach is the easiness of identified energy impact or other type of performance impact coming from the AFDD strategy. Again, because we assemble a baseline that is automatically learned from the historically collected data under similar weather and operating conditions. When the incoming snapshot data comes in, you really can very easily see the energy impact or other performance index changes. For example, this is when we identified a fault that is occurring, and you can clearly see that from the baseline, the energy is around the blue line region, and the red line is when the fault occurred. And the energy benefit analysis is kind of a byproduct of such a pattern matching approaches to perform FDD. We do see that at this point, the data-driven approaches is facing an even brighter kind of future, as we are all aware buildings are kind of equipped with many more data sources, including traditional BIS data, but also including many other emerging data sources, including security data, including the wearable IoT related device data. Seeing all these opportunities provided by the big data coming from buildings, our group is actively working with our collaborators from information science, trying to adopt or develop new AI strategies, especially for the time series data that buildings typically provide. One area that we're really interested in is more efficiently generating baseline kind of models. We are also often face questions such as how much baseline data is collection is enough. When there's new snapshot data coming from the buildings, how do you know that you have collected enough baseline data under similar weather and operating conditions? So we have just developed a new method using the correlation information entropy method, trying to answer such questions. We have published recently a conference paper, so if you're interested in the details, please refer to this publication. Basically, we use the information entropy to answer whether the collected information is enough. And if not, we don't rush into judgment and we wait until more information is collected. We're also trying to use different methods such as the robust multivariate temporal feature selection method that not only looking at the building time series data as an individual kind of isolated kind of incidents, but really looking at now if a current event, if event happens with say the supplier temperature, is that triggered by some other events that occurred a while back. So this kind of time related understanding about the feature plays a much more important kind of impact on the fault detection diagnosis for buildings. A very hot area that information scientists are actively working in is the so-called causal relationship learning. And we're working with the information scientists trying to understand how can we learn the relationship, what event trigger what event, mostly just by looking at data provided by building. Of course, another area a lot of people are working on is trying to use FDD method integrating with cyber attack kind of identification method to have a full understanding of the building performance. In conclusion, AFDD is very important, has a great potential to drastically changing or reducing the energy consumption of a building. However, there are major market barriers exist that have prevented the wide adoption of AFDD, especially the cost. The data-driven AFDD strategies have great potential to overcome those market barriers, yet there's still quite some development that can be done utilizing or developing new AI strategies specifically for our time series-based building data for better AFDD performance. And I really like to thank you for your attention, and the reference as well as our publications can be found under those links. And I will be happy to answer some questions.
Thanks, Jin, for that presentation. Despite the background noise, and I acknowledge you're on holiday at the moment, that was very impressive results and clear presentation. Seeing the 100% detection with negligible false alarms and stuff is really impressive stuff. I'm sure there'll be lots of questions on that. So people can feel free to put questions in the Q&A box there, and we'll come to those at the end of the presentations. So I'll pass directly now to our next presentation. So it's Associate Professor Mehdi Seyedmahmoudian, and he'll be presenting on data-driven approaches for building controls. He's from the School of Science, Computing and Engineering Technologies at Swinburne University, where he leads the New Energy Technology Research Group. And that's a team of more than 25 researchers focusing on renewable energy management and storage systems. He's published more than 170 journal articles in this field, and so we're privileged to have him presenting. And I will pass over to you now, Mehdi. Thanks.
Thank you very much, Stephen, and thanks everyone for actually attending this event, this great event. And thanks for the previous presentation, for a great presentation that she delivered before this. The short term of our presentation name would be data-driven approach, but the exact detailed project topic would be development and experimental implementation of transactive demand response management system through open ADR approach for institutional buildings. Thanks to IHUB, AIRAH, and Australian government for funding this project. I'm here to present this project on behalf of Swinburne University, CSIRO, BROMAC, and KIG Energy, which are the partner of this project. This is what's the topics of my presentation. We are going to actually talk about where all started, what is the transactive demand response system, what is the data-driven local EMS, data-driven community transactive energy management system, what are the data agents, which are the very critical points in this project, and how the DSH play a critical role here to actually achieve the full benefits of this project. Here is two of our buildings. So we have a fairly busy campus. So we have a lot of large buildings here. We are kind of in the urban area in Hawthorne. Obviously, you've heard the name because of the footy, but we are very in a very busy urban areas, and we have selected two of our buildings. We had more than 17 buildings to actually select for this project, but we selected a couple of buildings that we realized that they are very critical to improve the HVAC system. So as you can see, this is one building here that actually is a close-up picture, and this is the ATC building that are actually considered for this project. Where all started, during COVID, university actually came to analyze the energy bills. What's happening with the what's called the energy bills during and after or before pandemic, and they realized that even during COVID, where there was obviously lockdown. No one was in the building. There were some servers that had to be actually run during the lockdowns. However, most of our activities, classes, laboratories, events, all of them actually shut down. And they realized that not only we haven't actually saved energy during that period, it was in some specific zones of the buildings we actually actually consume more energy, and that was because of the specific appliances or users that had to be turned off, but they haven't been turned off, and they were running in the idle mode. That's actually they were using it during the whole period of the lockdowns. So this was a very, very great what's called significant point to see what's happening in the current institutional buildings. Having said that, we have discussed it with the current BMS, and that they are actually responsible for BMS of many of the buildings in these areas. And what we actually came up, we realized that there is a lack of data-driven approach in most of the institutional buildings, and obviously most of the commercial buildings that can be actually modified and can be actually improved with the data-driven approach that we are going to actually propose. We have proposed for this project. If we want to, apologies for some of the technical terminologies, I will make sure that I have a very clear explanation that is providing clear understanding for the terminologies. If not, please don't hesitate to ask me a question for any terminologies which is there. So in the existing building, if we classify that, obviously both of these buildings and most of the buildings that we have here, it was time scheduled set points. So during the day, they have the compliance, what's called user compliance assurance, that they need to make sure that at a specific time that there would be the set points of the temperature between 21 to 24 degrees centigrade, and then there is no lack of, there was a lack of actually receiving the closed loop signal from the zoning. So we had some zones, for example, they were either during the during the day, when we have, based on the timetable, let's say based on the schedule, based on the semester schedule, we didn't have any activities, but they were actually the HVAC system was operating where they didn't need to actually operate. We had some on-site generation, but the operation of HVAC system, which is up almost 65% of the total energy consumption within our buildings, were not actually considered the local on-site generation. So this lack of data-driven approach cost us fortune. As you could see in the previous slides, we were paying around, for only one section of the building, 60,000 a month for only energy consumption, which was based on the energy bill. So we came up with two approach, and actually two stage of energy management system. One of them was the data-driven local energy management system, which was based on, we identified more than 11 parameters that can affect the operation of HVAC system in a general building. However, for mostly more specifically for institutional buildings, they were internal, obviously internal and external temperature, occupancy rate, because we have against many of the commercial buildings, our occupancy rates actually are very varies during the day based on the timetable that we have. So we had occupancy rate, we have timetable, and local generation. Based on this, we wanted to prioritize our HVAC operating point and set points. The second stage that we considered, obviously this one, in a very, very general, simple language, this will minimize the energy consumption of the HVAC system using the data that they collect from the local controller collects from the building. And in the second stage, because we wanted to make sure that not only we actually reduce the cost of the HVAC system, but also we can provide the alternative and the energy resources, sustainable energy resources to actually for that operational energy consumption. So that's why we came up to the transactive energy market, transactive demand response systems, where you actually have the negotiation approach between the microgrids to buy and sell the energy, and you can actually have buy the energy from the grid when it's at its lowest price. So these two stages are actually the approaches that we considered for these projects. Let's look at the block diagram approach. This is the first level of this first stage, where you have actually your local energy management agents, and you have, which is based on different information, local forecasting agent, which forecasts the load and forecasts the generation. And then it provides this information for the local energy management system within that specific microgrid. Let's say, for example, building 1, they would say they would actually have this information about the forecasted load and also forecasted generation that we are providing using the locally installed weather stations. Then we have timetabling. Timetabling for many of the commercial buildings, as I mentioned, it's not very important because they are not actually emphasized on that. But for the educational building, for institutional building, timetabling is specifically important. For example, during the 10 to 12 or 9 to 11 a.m., we have highest what's called activities in our building, while from 11 to 1 we have actually a break, and then that actually affects the set points. Then we have obviously the backnet signal, which is for the BMS operation, and we have occupancy monitoring system that we actually discussed, and we are going to actually mention how we actually design this occupancy monitoring system. And we have local generation agents, which actually gets the signals from the local inverter to see how much energy they actually, what is the state of energy or state of the charge of the battery on that specific time. And obviously we have the weather monitoring system, which is for each building. Then
Mehdi, you've just got 5 minutes left.
Okay, so I have to actually go quickly.
Yeah.
So we have another microgrid for this project. As I mentioned, we are actually focusing on 2 buildings. So we have 2 buildings with a similar local energy management system, and then we go to the community microgrids, community level transactive energy management system, where you actually have the market agent. In this market agent, you communicate with the market operator, AMO in this case. You will get the state of the energy, you will get the instantaneous energy price for that specific time. You have obviously you have some community-owned generation system. For example, for this project, we had 30 kilowatts, 10 kilowatts for each building, and then 10 kilowatt, which was owned by both of them. So these community inverter or generator agents provides a state of energy for that community-owned asset. And these community market agents provide the estimated cost of energy that these agents have to actually comply with and provide the energy. I'm going to actually briefly explaining this one, how it let's say one bid and proposal, how does it work in our proposed transactive energy management system. At the beginning, you have the open TDR agents. You actually communicate with the AMO to see what is the energy price. You will receive the response back from the AMO, dynamic operating envelope that they have in the DNSPs and in the operational model. And then you will communicate this with all of these top level agents, which are market agents, community inverter agents, and community market agent, as well as each of the markets. They will process the signal, they will get the energy management, and they will reduce or manage the demand response within each microgrid. They will manage the demand response to its minimized level based on the information that they will get from here. And then they will see if they can actually have any specific zoning that they can turn off or turn on based on the information that they get from the Open TDR. For example, let's say let's say there is a request for the energy in this scenario. If you have the energy request for this scenario, which is with a good price, if this microgrid sees that this is a very good opportunity for me, instead of using it for my flexible loads, I can actually sell it to the grid or sell it to the microgrid to actually have the financial benefits for my own microgrids. Then in that case, they have the flexible zoning. For example, for our zone, for one of our buildings, we had 8 zones. Out of this 8 zones, we have 2 of our zones actually were flexible, that they can actually shift the loads. So they can actually turn them off or turn them down. And they can actually, instead of using the locally generated energy, they can sell it to the market. Based on this energy, you will actually send the response back to the Open TDR. The Open TDR will evaluate the signals, and then they will provide with the final frameworks that you can actually communicate with all of these agents can communicate with each other. For example, they will allocate the signal. You can actually sell the energy, 2 kilowatt energy to this microgrid. From this 1 kilowatt energy will go to the grids, and all of this calculation will be happening in Open TDR, will be transferred, the final signal will be transferred to the agents, and they will approve it and will go on. In the final, I will jump into the question. These are our zoning for the occupancy rates, that all of them are actually very experimental heavy. We install the different occupancy signals there, and we install the local forecasting, local data monitoring for the solar irradiance and temperature to forecast the system, which is really, really important, specifically for Victorian weather. And we have the timetabling approach. As you can see, only with timetabling, we could actually save 60% energy. Obviously, we cannot rely on timetabling only, but I just wanted to emphasize how important it is for educational institutional buildings to actually focus on that. And this is our solar, what's called on-site solar generation. Different scenarios we ran. Obviously, we are in the earlier stage of results. We have 6 months to go for final projects. And we could see only with community engagement and the auction pricing approach, we can actually save up to 16%, very conservative mode of the energy, of the actually total energy cost for the community. These are some of the results. Obviously, we don't have time to go through that. The most important thing in this approach, imagine that if we have increased all of these microgrids, all of this information, all of this the data information will be transferred to will be modeled in the DCH using the BRIC data standards, and we create the building semantic model. And in the DCH, you have access to all of the zones of the buildings, to multiple buildings that you can actually have within your community. In this case, it's only 2, but if we have actually multiple buildings, that would be really, really significant to have this data and run the what's called data analytic approach. Obviously, this is the conclusion. We can actually, using this approach, we are now, since 6 months we are in the project, we can increase the efficiency of the system, enabling community to enter to the energy market. This is really, really important for energy market and energy operator, prioritizing on-site and community energy generation, and making our buildings, and obviously, ultimately, our community resilience, which is very, very important in the current environment. And we have the data centering approach, thanks to DCH, that we can actually run our model our buildings there, and obviously accessible data that can be used. All of these benefits are coming with a cost. And obviously, the asset owners, the building owners have to be actually, there should be a motivation to actually move in towards a data-driven approach. Thanks to IHOP, thanks to AIRAH and Australian government that actually provide this funding, that we can showcase that novel algorithm, novel transactive demand response management system, novel open ADR approach can be used to provide a cost-effective data-driven approach and reduce the cost in a very sensible sense.
Thanks,
and
Mehdi.
Thanks to our partners.
Thanks very much, Mehdi, for that presentation. Good to see sort of both at the local level, just having the visibility makes such a big difference to 60% savings, but also to have that system level perspective as well is clearly critical. So I'll move on to the next speaker now. So TK Wang, he's the account manager at VBIS with over 15 years industry experience, focusing on building automation and technologies. He's taken on roles in engineering, project management, operations management, account management, predominantly in healthcare and commercial building sectors. And he's been involved in new technology solutions with a focus on stakeholder outcomes. Most recently in the field of asset management consulting services with VBIS. So TK is running Data Clearinghouse 7, working with City of Melbourne, and he can tell us a bit about the onboarding journey for buildings. Thanks, TK.
Thanks, Steve. Thanks, Stephen. So thank you for everyone for your time today. And what I'd like to cover today is essentially the onboarding journey that we've experienced today with DCH7. So just a bit of a background to start things off. The project partners involved in DCH7 were VBIS ourselves as the lead project partner, along with CSIRO and Predict, who are a technology company which focuses on building modeling and analytics. The aim of our project was to improve the accuracy of PV analytics and energy analytics in buildings using an open asset standard and data platform integration. What this essentially means was for us to try to build applications which could be reused and redeployable by querying the semantic model that is used in Data Clearinghouse in order to remove some of the friction points that we normally get to see when we are deploying new analytics. Through the use of the VBIS asset classification tags, we're also seeking to improve the data quality by providing an extra level of granularity which might not yet exist within the BRIC schema. The project was also supported by City of Melbourne, with them giving us access to 5 of their buildings for us to run these applications, interface into some of their sites and pull some of their data out to feed into DCH. So by way of a quick overview, the 5 buildings that we connected into were essentially 2 community hubs, a visitor centre and a library. And as you can see through the next few slides, the buildings themselves are reasonably varied. So in terms of size and the PV systems that were actually available to us. So at Boyd Community Hub, we were able to connect to 63 pieces of equipment, and access a 20 kilowatt peak solar system, with the overall controls being looked after by Delta Controls. Lady Huntingfield is the second community hub, which we were able to connect into. Now, this was a brand new building that only came online during COVID, during our lockdown, our most recent lockdowns here in Melbourne. The building itself, controlled by Schneider, with Schneider Controls equipment, actually allowed us to connect to 107 pieces of equipment, with about 900 points that we can monitor in total. Fitzroy Gardens Visitor Centre is a slightly smaller site, but with a reasonably sized PV system for us to try to pull some of that PVA data out of. Total equipment on site was only 35 because it is a reasonably simple visitor centre with a cafe on the side. However, we are still able to get quite a few good data points out of this. The next 2 are actually libraries. So again, this gives us an ability to compare 2 types of buildings, at least within our data set. So we have obviously 2 community hubs, and this is the first of the 2 libraries, where it's a 10.4 kilowatt peak system. Delta Controls 20 bits of equipment connected with about 250 data points. And the last one here is Library at the Docks, which was an 85 kilowatt peak system. Now, unfortunately, the building is actually currently undergoing a BMS upgrade. So we haven't been able to connect to this building just yet, but we anticipate to be able to access the site within the coming days. In terms of network topology for our deployment, what we have actually done is try to keep a reasonably standard method of deployment. So for every single site, we've looked to deploy a gateway, which will communicate to DCH via a 4G router where we couldn't get internet connectivity, and with one site where we were actually able to utilize the existing site infrastructure. All the communications will go back through the MQTT protocol. And for the solar information, what we have done is we've tried to tap into the APIs that are currently available. Now, these did present their own challenges, which I'll cover a little bit later on. Once the data is actually stored within the DCH, the predict applications will actually query the DCH model for the semantic information before getting the time series data out of DCH to run their applications. In terms of deployment progress to date, what we've been able to, we have been delayed by the current lockdowns, unfortunately, but what we have, with the project starting just before the last lockdowns took effect, but what we have been able to do to date is provide the equipment tags based on the VBIS asset classification standard and for incorporation into the BRIC model. CSIRO have been able to build the semantic models already using the BRIC and enhanced it with the VBIS tagging, and Predict have developed the applications which they need in order to model the building and provide PV and energy performance recommendations. Now, what this has enabled us to do is to take these pieces, bring it all together, and really help try to reduce some of the barriers that we normally see with the adoption of new systems. In our deployment, we do come across some learnings, and these are the main points that we'll probably be going through today. Broadly speaking, we've grouped them into two categories. The first being data access and data quality. Despite there being some documentation available for every site information availability was one of the key challenges that we had when trying to allow for the while trying to build the data models within DCH. Every site was built by different contractors at different times, and while we were generally able to reverse engineer or work with different data sources to get to the right information, it wasn't a straightforward exercise where we could get a single set of data in order to build the models. The second point I'd like to mention in our data access and quality is primarily around network and system integrations and the understanding of how these come together. So a typical building, typical facilities teams will have a very good overview of how the system operates and who the contractors are which maintains the systems. However, detailed understanding of system connections, configurations, and things like that normally reside within the contractors. Will normally reside with the contractors themselves. However, when we're looking at a building model and we're looking at how we pull data between different systems, where this currently falls short is that each contractor will have very detailed knowledge of their specific bit of equipment, but very little knowledge about how that equipment potentially gets handed over and used in a different application. Third point on our data access and quality that we came across was what we probably call open doesn't necessarily equate to accessible. So what we mean by that is if we're looking at BMS data points, all the controllers that were installed on site were BACnet compliant open protocols controllers. However, there's still a lot of flexibility for BMS contractors to decide what points they choose to expose on their platform. So while there were points where we really expected to be available through the gateways that we installed, what we eventually found was that some of the points were not actually exposed. So available on the BMS can see all the data points, but we couldn't actually pull the same data points out of the BMS system. The same thing really happened with the APIs for the PV system. So in the PV web portals where you can go in and get a lot of data, we could see that there was a lot of rich data that has been stored by the PV system. However, when we tried to interface into the system using the APIs, the data points become significantly more limited, thereby restricting what we can actually pull out of the system themselves. The next thing we really came across that presented some challenges was around how BMS systems configure history. So Predict required a lot of the data models. To build their data models, we required a lot of history data. Not all BMS systems configure history information in the same way or will have access to the same level of history, which could impact how models are actually built and configured in the first place. Limitations that we came across generally included sort of duration in terms of how far back we get to populate our model, and also just how the BMS history points are actually configured. While in a normal time series system, we would expect to see fixed time durations for data points, some BMS systems are actually configured using change of value. For normal operation, we wouldn't consider that to be a big issue. However, that then does create additional uncertainties, and that we wouldn't know if the BMS system actually lost comms with that point, which is why we stopped getting access to that particular data point, or whether that data point just hasn't moved. And the last point that we sort of grouped within the realm of data access and quality was around metering data and availability and granularity. So again, we understand that new buildings, as they get built, a lot more effort is put into metering and making sure that each system is metered correctly and that data is available for other systems to consume. However, with older buildings, especially with the existing infrastructure that we currently have, some of that metering data is not always available, which also impacts the ability for us to run detailed analytics that we have hoped for. The next general grouping that we sort of come across from what we can see in our delivery so far is what we consider process considerations. So these are things that we probably need to start considering as we transition towards smart buildings, digital buildings, and the infrastructures that are required to support them. So the first one is around equipment maintenance and the impact that these have on connected systems. And I suppose one way to look at this is currently, if your light bulb fails, you'd swap out the light bulb, light's still able to turn, you can turn on the light again and away you go. But with smart systems and smart buildings now, it's no longer a case of just replacing the light bulb. There are more considerations that need to be taken into account, especially around how that data point, if that smart light bulb doesn't need to have its IP address reset, doesn't need to have its configuration files reset as well. We actually saw this in real life. So with one of the City of Melbourne PV microinverters that had failed on site, it was replaced on site. This was a building that we had already connected into and configured within DCH. What we actually found was that in replacing that microinverter, the PV system was able to understand that it was a new microinverter with a new microinverter ID number. And from a PV system, it works. They had no issues connecting to the point again. However, what we noticed was that the data point went offline. And it was only through investigations that we identified that that there was a fault with that particular unit. The unit was replaced, and there's now a new ID associated with that. Which leads into the second point of data being treated as an asset, with processes designed accordingly to treat it as an asset. So this is really looking at a system and now saying it's no longer about just replacing the physical asset, like I mentioned before, but we need to treat data as a standalone asset that needs its own processes and its own processes in order to ensure that we don't have these data breaks as systems change. Now, this is very much a different mindset to how it's currently done, and it probably needs to fall more in line with how IT systems are currently treated. The third point on our list was locating data sources available within DCH. So one of the big points that we were looking for, especially around the PV data, was around access to weather data. Now, the weather data that BOM have was quite extensive. DCH had access to all of them. However, a lot of the data points that we were looking for might resided in multiple data sets, and understanding how to get access to a lot of these data sets presented challenges in itself. So one of the things to understand as we start to link into infrastructure such as DCH would be to understand how applications can best get access to that data. And the final point we have here is around identification of skills and resources required to maintain these models. So currently, a lot of these, what we consider semantic modeling, there's been a lot of discussion that's been around upskilling existing resources, such as BMS contractors, to undertake the semantic modeling tasks to make software providers, analytics providers, roles a little bit easier when it comes to onboarding and getting access to that information. While this would work for building services that BMS providers interact into, when we're trying to build a semantic model for a whole building, this potentially requires an additional skill set. So somebody who actually understands all aspects of a building, not just services that generate data. So this is something that potentially needs to be considered when we start to deploy on a wider scale, to say, how do we actually manage this process, when systems need to be updated, when data points change, who is actually the best people to maintain these semantic models. I guess for us, given we've really only just hit our first milestone, which was try to connect a lot of these buildings. But for DCH7, the next steps for us now is to actually connect to Library at the Dock in the coming few days, now that the BMS system has been upgraded, confirm the MMV tasks and deploy the applications, start using the Predict applications to live stream a lot of our data, implement a lot of this feedback, and actually start to demonstrate the improvements that we can achieve using these open data standards, the more detailed semantic modeling that we can generate with the VBIS tags, and really demonstrate that applications can become a lot more reusable through use of a platform such as the Data Clearinghouse. Thanks.
Thanks so much, TK. That's fantastic work there, and some nuanced learnings from all your hard work going into these buildings. If people should feel free to drop questions into the Q&A functionality there. We've got a few minutes left. We're probably a little bit over time. And just while we're waiting for Q&As to come through, I guess one of those flavors in this data-driven smart building space is, to what extent is this an IT industry challenge versus an HVAC challenge? And so really I'd put it out to all three speakers there. What do you think? Should we all be IT engineers?
Stefan, I can talk first. I do want to apologize for my background music. I didn't realize how loud that was. Somehow it's really magnified. I totally agree with you, Stefan. A lot of times the IT challenges, from my viewpoint, seems to be even stronger than a lot of times than the field experts face the challenges. I have currently a project till now. Despite all the data strategies, we still couldn't send the command because of the firewall issues. However, I do hope that IT barricades can be resolved in a fair near future. And after the IT challenges are resolved, then how do you really analyze those data, and how do you really convert from data all the way to wisdom, as your Annex 81 has really beautifully described? I think that becomes the upcoming challenges I think we're going to face very soon.
TK, did you want to comment?
Yeah, I think we are really at that point where there's a lot of convergence, right? So we have IT providers that are now slowly moving into smarter buildings, digital ceilings, and the likes. And we also have a lot of traditionally your building services companies moving into the software space. So I think in terms of where this is heading, it is likely to be somewhere in the middle. But it's likely that we will require skill sets from both industries in order to make this work. Because if we consider this a pure IT data science issue, while we might be able to build beautiful models of how buildings operate, there will be a practical aspect that's actually missing from a lot of this. And I think we will fail to get a lot of the insights and that wisdom that we really hope to achieve. On the other side, if building services companies don't start treating this more like an IT problem and facilities managers and operators don't start seeing this data as and treat it with the same respect that they give IT systems, we're going to find that it's very hard to maintain these systems. And we lose a lot of that value as well as we go down the path. So I think this will be a converging of industries, hopefully to the benefit of both.
Thanks, TK. So another question, I'm always fascinated by the need for ground truth in data-driven systems. And, we have events like COVID coming along, and suddenly buildings are completely different, operated in different ways to the way they were before. I guess what's the right amount of data that we need? And how do we deal with changing conditions and events inside buildings? I don't know, Mehdi, did you want to have a first go at that?
Yeah, absolutely. I would actually answer the first question that you asked, because it is a very interesting approach, interesting question that you asked. And I really believe that this problem, the data-driven is actually both data, both IT and engineering. And but what I could say is that the first stage is IT. So you need to actually have the information. You need to have the visibility about the buildings in order not to be blind about what's happening within your buildings. And in fact, when you get the information, then you assess it. Then the reaction for that dot for the data that you get from the building is that is the engineering work that needs to be done in order to improve the system. And this is also kind of an answer for the second question, that we believe that visibility is the main key to actually have the dynamic approach for our building performance. And the dynamic approach and resilient approach is where we are actually protected in the time of in different occasions. For example, during the lockdown, if we had this approach, we could actually save a lot of money using the data that we collected from the building. So I really believe the first stage would be the data, and then with the reaction that we will have to using the engineering approach to maintain the accurate data, and then providing the corresponding action for the building performance system. It would be the engineering.
Mehdi, and Jin, is ground truth the ability to get hold of ground truth data? Is that a serious problem for data-driven approaches?
So personally, for researchers, I do think having ground truth is very important, just for us to understand the accuracy. Now, once you're applying a strategy in the field, I don't believe ground truth can really be identified because it's ever passing kind of event. So from that perspective, I don't think ground truth is as important as the so-called baseline. And I define baseline as a status when you are happy with the building performance. It's like human being. You can never find a 100% healthy person, but at a status like you are happy, the doctors are happy, that is the baseline. And then you compare with other performance against this baseline performance. And back to your data question, personally, I don't think the amount of data is a good index to evaluate. That's why we have developed and we have been using the so-called entropy concept to evaluate typical information science concept. Really is evaluating how rich your data is. You can give me a lot of data, but you may not provide enough information for me to really make a decision. So as I agree with the other two speakers, really need to converge the information science with our building science. Now, one more thing I find very interesting and also trendy is how do you incorporate the existing physical knowledge, including even differential equations, into the information science domain? And there are quite some researches along that direction. So it's another line of information pulling in coming from our collected wisdom in the past hundreds of years. So I think that's another interesting perspective facing us right now.
Mm. Thanks, Jin. And TK, from your perspective, how much data is the right amount of data, or what data is it that makes it that's going to make a difference?
I think similar to what Jin has said, I think it's about rich data as opposed to data quality, because in terms of data, if we think of how buildings are controlled, the reaction time of buildings is generally quite slow. So we don't need second by second data in order to run good analytics. But what we do need is consistent data. What we do need is to be able to retrieve that data when it does become available. So I think there is a diminishing return as you start to get to, especially around how much data we collect. but there is going to be a minimum amount that you would consider to be fit for purpose for what you actually need in order to run your analytics. And then really after that, it's really about how much granularity would you like. So if we think a typical building, a typical BMS system, maybe every 5 minutes is sufficient. You wouldn't need to go down to a 6-second sort of data sampling like you would in an industrial platform. So it is really dependent on application.
Cool. And I'll finish with a question, probably works well for Mehdi and Jin, which is sort of, particularly Mehdi, you've used the game theory approach and with agents and stuff. Would you expect to get some emergent kind of knowledge that is beyond what you would just simply know by knowing the tariff structure of the individual owners? You know, would you see something really interesting just emerging out of something that comes from machine learning or data-driven approaches that you wouldn't have otherwise known?
Actually, yes. Like, for example, now using this system, we are actually learning how the operating envelope of each agent, whether they can be synchronized, because in many of the research papers that you could see that they have a microgrid, that within that microgrid, that the demand that in most of the commercial building, the majority of the demand would be for HVAC system. And they want to actually comply with the dynamic operating envelope that AMO has and the grid has. And they assume that these two dynamic operating envelopes can be synchronized. Using the data that we get from our system for our buildings, we are actually reaching to the point that for some of the elements and for some of the time of the day, you cannot actually have the synchronized operating envelope. And there has to be some standardization within the community in order to make sure your community operating envelope is synchronized with the dynamic operating envelope that the grid has. So yes, and this achieves, in order to actually make sure that there is a compliance between all of the operating envelope, you need the AI, and we are actually reaching to the point that the coefficients that has been measured in the previous research that we see in the literature, some of them are not based on the experimental approaches for the commercial building. So for the commercial and educational building, those coefficients has to be changed.
Thanks, Mehdi. And that sort of idea of emergence, where at a granular level, things behave differently when they become a system level. Jin, I mean, probably it's a little bit outside of what you've traditionally been doing in that sort of agent-based thing, but perhaps you'd have some thoughts on that.
Yeah, so I personally haven't done any agent-based kind of game theory control yet. But even with somewhat simpler data predictive kind of control, we have also found that for building that we're doing right now, data-driven control, we have run the model, generated the right set points, but then very soon you can see that you can learn the heuristic rules from those model predictive control. It's fairly straightforward for a lot of conditions. So I do think there's a potential that you don't need to always run a complicated computational intensive control for every scenario. So a lot of times you can learn simpler rules and just implement those heuristic rules.
Yeah. Excellent. Thanks so much for a wonderful session. Jin, Mehdi, TK, great presentations.